Hello and welcome back again to this lecture series on powder metallurgy. Right now we are discussing a very important property of the powder, that is the surface area, and this is important because the surface area correlates to a range of particle properties which affect various phenomena involving the powder particles, including the compaction and the sintering process in powder metallurgy, right? So when it comes to measuring the surface area, the BET method stands out, and we have seen that the BET method is based upon the adsorption of a gas on a solid surface. And with regard to that, we discussed about the Langmuir adsorption theory, which basically considers the adsorption process, that is the binding of the adsorbate molecules on the adsorbent surface, as a chemical reaction where the adsorbent surface is considered as a homogeneous surface in which these adsorbate molecules attach in specific sites, okay? And from that we derive this surface coverage, and from that we have derived an equation or an isotherm which correlates the amount of gas which is adsorbed on the solid surface to the gas pressure, okay? And ultimately this forms the basis of the BET technique. So let us continue on this in today's class. All right, so in the last class we learned about the Langmuir Isootherm, which basically talks about the formation of a monolayer on a solid surface when the gas is being adsorbed on the surface. And the surface coverage was defined by a parameter called theta, and then we derived the isotherm and saw that theta increases with P, and then ultimately it saturates when theta becomes equal to 1. The corresponding equation for this isotherm is given by this. Right, so when it saturates and theta becomes 1, that means the entire surface is covered by the gas molecules and a monolayer is formed, right? And that can be depicted by this picture also over here. So in the beginning, the gas molecules are adsorbed on the solid surface at specific sites, and that's how we define the theta as the surface coverage, which basically talks about the adsorption of these molecules on specific sites on the adsorbent surface. Now, as the pressure increases, more and more of the gas molecules get adsorbed on the surface, and then at some point it saturates when theta becomes 1, and that is what you see over here, and this corresponds to this saturation, as you could see over here, when theta is 1, right? And from this we have also derived the equation which correlates the pressure with the volume, and that equation is given as this. Right. So here Vm is the volume of the gas corresponding to the formation of the monolayer. Now coming back to this BT surface area, that is basically an extension of this Langmuir isotherm, wherein instead of a monolayer, the layers beyond that, that means formation of multi-layers is considered, and this isotherm equation is modified accordingly, and this equation then can be used to calculate the specific surface area. But before we come to that, let us also have a look at the different types of isotherms. So depending on the interactions between the adsorbent and the adsorbate, there could be different types of isotherms. So let us talk about that. There are basically 6 types of isotherms depending on the interactions. This one is type 1, which is basically the Langmuir isotherm. And this is also reversible type, which is typical of microporous solid surface. Right, so this interaction between the adsorbent and the adsorbate will depend on the condition of the surface, especially with regard to the porosity. And in terms of the porosity, the solids can be categorized into different categories depending on the size of the pores. It is called microporous when the pore size is up to 2 nanometer. If the pore size is from 2 to 50 nanometer, that is known as mesoporous. And when the pore size is more than 50 nanometer, that is known as a macroporous solid. Okay, so this is how the solid surface can be categorized based upon the size of the pores. Now here you can see one more type over here in the isotherms. This is type 1A, which is opted for materials with wider micropores and narrow mesopores. Okay. So the first type That means type 1 is typical for materials with pore width around 1 nanometer, and this 1A is for materials where the micropores are wider and they also have narrow mesopores less than about 2.5 nanometers. Okay, so depending on again the size of the pore or the width of the pore, the type 1 can be of two types. The next one is type 2, which is here. This is also a reversible type isotherm as shown by these arrows. And this kind of isotherm basically correspond to materials that are non-porous or macroporous. Here you can see a bend over here at this point. Let's say we call this point M. So that point M basically corresponds to formation of a monolayer. And when the monolayer coverage is completed, the curvature is changed as you could see from here. And it becomes quite steep as opposed to a gradual change over here till the monolayer is formed. So this kind of indicates the formation of multi-layers when it goes beyond the monolayer and then the curvature starts to change. This is indicative of the beginning of the multi-layer adsorption process. The next one that you see over here is type 3. This kind of isotherm is formed, the type 3 isotherm, when the interaction between the adsorbent and the adsorbate is weak. Okay, so type 3 kind of isotherms are obtained when the interaction between the adsorbate and the adsorbent is weak. So here the interaction between two adsorbate molecules approaches that between the adsorbate and adsorbent, okay, which also means that the heat of adsorption is similar to the heat of condensation. So therefore, for this kind of interaction, a significantly high partial pressure of the gas is required for the adsorption to happen. And this kind of isotherm is associated with large pores. Next, we have type 4, which is over here. And in this also, there are two categories, A and B. So type 4 basically is a variant of type 2 with hysteresis, as you could see over here. The hysteresis is formed here. And these two types that you have here, A and B, they are basically related to the width of the pore, which is present on the surface of the adsorbent. If the width is higher than a critical width, which is related to the material's adsorption characteristics and temperature, then 4A type is obtained. And on the other hand, type 4B is observed for materials having mesopores of smaller widths, and this type is common for mesoporous materials. With pores of smaller width. Then we have type 5, which is here. This is similar to type 3, but with hysteresis, as you could see. There is a hysteresis here, right? This kind of isotherm is found at low relative pressure and is associated with mesoporous materials. And this kind of shape of the isotherm can be attributed to the weak adsorbent interaction. So here also the interactions between the adsorbent and the adsorbent are weak. At high relative pressure, the hysteresis can be observed. And here molecular clustering is followed by the filling of pores or the capillary condensation, right? So that is associated with this kind of isotherms of type 5. Then we have this type 6 here. Type 6 isotherm is typical for multilayer adsorption on materials which have highly uniform non-porous surfaces. And the curve that you can see over here is like a step-shaped curve, and each of these steps corresponds to a monolayer, and the nature of the curve will depend on the material, the gas, and the temperature. Right, so before we wind up today's class, let us take a moment to summarize this lecture. So in this lecture, apart from the Langmuir isotherm, which represents formation of a monolayer, we have also seen other types of isotherms. Depending on the physicochemical interactions, there could be different types of isotherms, and these are type 1, in which you have two types, 1 and 1A. Type 1 is basically the Langmuir isotherm and corresponds to materials having pores with small width in the range of about 1 nanometer. And the second category of type 1, that is 1A, is typical for solids which contain both wider micropores and narrow mesopores in the order of about less than 2.5 nanometer. Type 2 isotherm corresponds to materials which are non-porous or macroporous. And in this case, we had seen an inflection point M, which indicates the monolayer coverage, and beyond that point, the multilayer adsorption starts to happen. Type 3 isotherm is obtained when the interactions are weak, and in this case the interaction between two adsorbate molecules in fact is similar to the interaction between adsorbent and the adsorbate, or sometime maybe even higher than the interaction between the adsorbate and the adsorbent. Type 4 we have two categories A and B. When the width of the pore is greater than a critical width, type A is obtained. And type B is typical of mesoporous materials having pores with smaller widths. Type 5 is same as type 3 with hysteresis, and in this case at higher relative pressure the hysteresis is observed, and one typical characteristics of this kind of isotherm is molecular clustering and pore filling or capillary condensation. And then finally we talked about type 6, which has a step-like isotherm, and here each of the steps represents a monolayer coverage. So this is typical of multi-layer adsorption. Okay, so with that we come to the end of this class. Thank you for your attention.